Engineering analysis of lithium-ion battery thermal runaway. For the introduction, we have the uh, thermal runaway is a major safety concern in lithium-ion batteries. It occurs when the heat generated inside the battery exceeds the heat it can dissipate, causing a self-sustaining increase in temperature. So this can lead to electrolyte decomposition, gas release, fire, or explosions, making it a significant challenge for the safe use of high energy density batteries in electric vehicles with energy storage and portable electronic devices. Now, for the failure mechanisms, thermal runaway is initiated by external abuse, mechanical damage, overcharging, short circuit, or overheating, or internal defects, dendrite growth, manufacturing flaws, or separator failure. So once triggered, it progresses through three stages: uh, solid electrolyte interface layer decomposition, 180 to 120 degrees Celsius, electrolyte decomposition and reaction with the anode, 120 to 200 degrees Celsius, and finally cathode oxygen release combustion above 180 to 250 degrees Celsius. So resulting in a rapid heat generation and potential fire or explosion. So the reaction driving thermal runaway are strongly temperature dependent and follow erroneous kinetics, causing heat generation to increase rapidly once critical temperature is reached. So the process is modeled using an energy balance equation where the battery's rate of temperature change equals the total heat generated from joule heating and exothermic chemical reactions minus the heat dissipated to the surrounding. The heat generated by its reaction is described by the Arrhenius Bayes equation that depends on reaction enthalpy, activation energy, temperature, and the extent of the reactions. So we have also the advanced analysis uses multi-physics 3D finite element models, COMSOL, ANSYS, coupled electrochemical thermal models, thermal propagation models for battery packs. Uh, okay, engineering parameters, thermal runaway onset temperature typically 150 to 200 degrees Celsius. Depending on the chemistry, LFP is significantly more stable than NMC or NCE. So we have the heat release can exceed 100 to 300 kilojoule per cell. In propagation risk, heat transfer to adjacent cells can trigger cascading failure in modules. So the thermal runaway can be mitigated through engineering solution at multiple levels, safer battery materials, protective cell components, advanced pack level, thermal management, and intelligent battery management systems with early fault detection and automatic shutdowns. The overall design goal is to keep battery temperature below critical limits and prevent failure propagation. Battery safety is evaluated using calorimetry test, DSC, and arc abuse test, nail penetration, overcharge and crash, and compliance with industry safety standards such as UL 1642, UL 2540, and SAE G2464, and IEC 62619. So we have the IEC means International Electrotechnical Commission, and SAE, Society of Automotive Engineers, and UL stands for Underwriter Laboratories. So we have the conclusion here. The thermal runaway remains a fundamental engineering trade-off uh, between density and safety. So continued progress in multiple scale modeling, advanced materials, and intelligent thermal management system is essential to enable safer, higher performance lithium ion batteries for widespread electrifications.